Integrals are another super useful mathematical operation that pops up all the time in physics. And one way to think about them is they're the opposite of derivatives. They undo everything a derivative does. So if you recall what a derivative is going to do, if we take the derivative of an equation, say b times t to the n plus some constant, what we're going to get out on the other side is b, that constant, and then we multiply by the power of t, and then we subtract 1. Oops, not add. We subtract 1 from t's exponent. And then this constant, well, once we take the derivative, it's just 0, so we don't even write it down anymore. So that's how we do a derivative. And the integral is going to be just the opposite of that. If we want to take an integral, then we write it like this, sort of S-looking thing. That's because an integral is actually a type of sum. So we have this S, and we have dt to remind us with respect to t. And then we'll take it for the equation a, just a constant number, times t to the n. And what that's going to be equal to, we're going to do the opposite of everything we did here. So we have a, that actually does stay the same, but then for the power of time, over here for the derivative, we subtracted 1. So when we do the integral, we're going to do the opposite. We're going to add 1 to the power, so it'll become t to the n plus 1. And then over here, we multiplied by the power of t, and here we're going to divide by it. Over here it was the derivative, it was the old power. Over here for the integral, it's the new power. So it's n plus 1. And then over here for the derivative, we had a constant, and once we took the derivative, it became 0. Here, we don't have a constant. We're adding 0, would be mathematically equivalent, so we have to make sure that we add a constant back in. So this is a new unknown constant that shows up when you take an integral. And a lot of times, if you want to use this, you're going to need more information to figure out what number this actually is. There isn't enough information just in this equation to figure that out. So let's do an example with some numbers. Say we want to take the integral of this equation, 4t squared. So the 4, that's the same place as the a here. That's just going to stay. T to the second power, so we increase the power by 1, so this is going to become t to the second plus 1, and then we divide by that new power. So here, 2 and n, they're playing the same role, so we're going to divide by 2 plus 1, and then we need to add a constant. And even though we've got numbers here, we still don't know what this constant is, but we know it may exist and it may not be 0. So then we'll clean this up. This is 4 over 2 plus 1, so 4 over 3, so 4 thirds. This is t to the 2 plus 1, so t to the third. And then we can't do anything about this unknown constant d, so we just have to leave it there. So that is how you do an integral. Let's try another case. Let's do a new example. Let's take the integral of this equation. So we have, let's say, 2 t to the third plus 6 over t squared plus 4. All right, so we need to change this up a little bit because not all of these terms look just like that term, but we can rewrite it so they will. So this is the same as taking the integral of, well, don't need to do anything like this. It looks just like that form. It's a constant times t to a power. This guy we do need to redo, but dividing by t to a power is the same as multiplying by t to the negative of that power. So this is equivalent to 6 times t to the negative 2. Here we were dividing by t squared, here we multiply by t to the negative 2, and those are mathematically the same thing. Now 4, that's a constant, but this is equivalent to 4 times 1. I think you'd all agree with me there. So 4 times 1 is 4, but 1 is also equal to anything to the 0th power, including t to the 0th power. So now we are ready to take the integral here. Okay, so 2, that's just like a, that stays in front. T to the 3rd power, we're going to add 1, so that's t to the 3 plus 1, divided by that new power, 3 plus 1. Plus next term, 6, t to the negative 2 plus 1, divided by that power. It's negative 2 plus 1 here. And now you can see maybe why I did it this way. I have 4 t to the 0, the old power, plus 1, divided by that new power, 0 plus 1. And then, of course, we do have the constant that we've always got to write. All right, now need a little more room. Oh, that's not great. Maybe we can move this. All right, just a little bit more room, and we can clean this up. All right, 2 over 3 plus 1, that's 2 over 4. T to the 3 plus 1 is t to the 4 plus 6 over negative 2 plus 1, that's negative 1, t to the negative 1, plus 4 over 0 plus 1, that's 1, t to the 1, plus the constant that we don't know, and we can clean this up even a little bit more, 2 over 4, that becomes 1/2, 6 over negative 1, that becomes negative 6, t to the negative 1, well, that's the same thing as dividing by t. And then 4 over 1, that's 4. All right, and I guess we don't need to write this exponent either. It's implied when we leave it as just t. So if you're integrating this equation, here's what you end up with.